All right, welcome class. In our previous sessions, we've really laid the groundwork, right? We've talked about foundational economic principles, we've gone through management theories. Well, today is where we bridge all that theory with some powerful practical application. We're going to explore how a branch of math you might remember from an abstract algebra class, matrix mathematics, actually becomes one of the most critical tools in any modern manager's toolkit. And look, this isn't just about solving for X and Y. It's about making decisions that are defensible, that are optimal, and that are profit-driven. By the end of our time today, you're going to see exactly how the numbers you model on a spreadsheet can translate directly into a company's real-world performance. So here's our game plan for today. We're going to follow a very logical path. We'll start with a real-world business problem, the kind of profit maximization puzzle that you will absolutely face in your careers. Then we'll learn the language we need to frame this problem, the language of matrices. After that, we're going to get our hands dirty and build a production model, step by step. And once that model is built, we'll find the best possible answer, the optimal solution. Finally, and this is so important, we'll talk about how to avoid the common mistakes that can turn this powerful tool into a source of some really costly errors. Okay, let's jump right in. I want you to really put yourselves in this position. Imagine you're the operations manager at a manufacturing plant. Your main goal, the one the board is judging you on, is to maximize profit. Simple enough, right? But you live in a world of limits. You don't have infinite resources. These are hard constraints. You've got a set number of labor hours every day. Your machines can only run for so long. Your raw materials are finite. So the real challenge, the puzzle you have to solve every single day, is how to allocate those scarce resources to hit your main goal. This isn't a textbook problem. This is the reality of business. So this is the question, isn't it? It has to be on your mind constantly. You're looking at a bunch of different products you could make. They're all profitable, but you can't make all of them. Now, the temptation for a lot of managers is to just go with a gut feeling, right? Or maybe they'll just make more of whatever sold best last month. But those methods are, well, they're unreliable. They're not rigorous. What you need, what a successful business demands, is a systematic, data-driven way to find the single best plan, the one that squeezes every last possible dollar of profit out of your operation. Okay, so let's set the stage for our scenario. To make things clear, we're going to work with a simplified system, just 2 products. Now, I want to be very clear about this. The logic we developed today for 2 products scales perfectly to a massive factory with 2,000 products. The math gets more complex, sure, but the fundamental challenge is exactly the same. How do we balance the production mix to get the absolute most profit we can, given the resources we have? So how do we do it? How do we take this complex, kind of messy, real-world problem and turn it into something clean, something structured that we can solve with absolute precision? Well, we need a new language, a formal language designed specifically for this kind of problem, one that can handle all these different variables and constraints. And that language, as you see here, is the language of matrices. The specific technique we're going to use is called linear programming. Now, I know that terminology can sound a little intimidating, but don't let it fool you. This is one of the most powerful and widely used tools in the business world, in everything from finance to logistics. The word linear is the key here. It just means we're assuming the relationships are straightforward, like making 2 widgets takes twice the resources as making 1. And programming here doesn't mean computer coding. It's an older term for planning. So just think of it as a structured way to plan for the best possible outcome when you're dealing with a bunch of constraints. And it all comes down to this beautiful, elegant little equation. A, X equals B. Now, its simplicity is really deceptive because inside these 3 letters, we can pack our entire business problem. The matrix A holds all of our production rules. The vector X is where our decisions live, what we choose to make. And the vector B represents all the stuff we have to work with, our resources. This is how we get clarity. This is how we go from a messy business problem to a clean, solvable math problem. Let's really break this down because getting this right is everything. A, you can think of that as your technology matrix. Each number inside it tells you exactly how much of a resource, say labor hours, you need to make 1 unit of a product. Then you have X, that's your decision vector. Those are the numbers you as the manager get to choose. How much of product A will we make? How much of product B? And finally, B is your resource vector. That's just a list of your totals, how many labor hours you have in total, how many machine hours, and so on. Mastering this translation from business speak to math is the absolute key. All right, enough with the abstract theory. Let's get our hands dirty. We're going to take that formal structure, AX equals B, and we're going to fill it in number by number using the data from our company scenario. We have to be meticulous here, because you're about to see that in business math, every single number matters. Every number has a direct link to the real world. Building any good quantitative model, it doesn't matter if it's for production or marketing or finance, it always follows these three logical steps. First, you have to define your variables. What can you actually control? In our case, that's the number of units of product A we make, we'll call that X, and the number of units of product B, which we'll call Y. Second, you have to state your goal, your objective. It's not just make money, it's to maximize profit, and we're going to write a specific function for that. And third, this is the real core of it, you have to map out your real-world limits as mathematical constraints. Okay, take a look at this table. This right here is our blueprint. It has all the critical information we need. Let's just walk through it. Look at that first row, labor. It's telling us that to make 1 unit of product A, it takes 2 hours of labor. For 1 unit of product B, it only takes 1 hour. And in total for the day, we only have 10 hours available. See? The second row does the exact same thing for machine time. And that last row, that's the money. That's our profit margins. $40 for every A we sell, 30 for every B. Every single number on this table is about to go into our model. So using that financial data from the table, we can now write what's called the objective function. This is just the mathematical sentence that describes our main goal. As you can see, our total profit, P, is simply $40 times X, the number of product A's we make, plus $30 times Y, the number of product B's we make. Our entire mission, the whole point of this exercise, is to pick the perfect values of X and Y that make this P as big as it can possibly be. Now for the rules of the game. Our limitations. Let's look at the labor constraint. We know each X uses 2 hours and each Y uses 1 hour. So the total labor we use is 2X plus Y. And since we only have 10 hours available, that total has to be less than or equal to 10. Same exact logic for machine time, X plus 3Y has to be less than or equal to 12. And then we have these last two. They might seem super obvious. Of course, you can't make a negative number of products, but mathematically, they are absolutely essential. Forgetting these non-negativity constraints is one of the most common mistakes students make, and it leads to answers that just don't make sense in the real world. And there it is. This is that moment where it all comes together. We have officially translated our business problem into the language of math. You can see it, right? The coefficients from our inequalities, the 2, 1, 1, and 3, that's our A matrix. Our decision variables, X and Y, that's our X vector. And our resource limits, the 10 and 12, well, that's our B vector. Our qualitative business challenge is now a perfectly defined mathematical problem, and it's ready for us to solve. So, we've built the model. And honestly, that's often the hardest part. Now comes the payoff. We solve this system. And you've learned a few ways to do this, graphically or using matrix algebra, and we get our answer. But it's not just an answer. It's not just a good plan. What we get is the single optimal solution, the best possible decision. And this is it, $220. After all the calculations, this is the number. This is the absolute maximum profit our company can make with the resources it has. It is not an estimate. It's not a guess. It is a mathematical certainty. The profit can't be $221. It's impossible. And for a manager, that number is gold. It's a benchmark. If your factory is making less than that, you know there's a problem somewhere. You know there's room for improvement. So what does that $220 number mean in practice? It translates to this right here, a specific, actionable instruction. The math tells us, without a shadow of a doubt, that the best possible plan is to make exactly 4 units of product A and 2 units of product B. That's the memo you send down to the factory floor. Any other combination of products that fits our constraints will, by definition, make less money. The math gives you the definitive directive. And this slide right here is why we do the math. This is so important. Let's imagine a manager just goes with their gut. They might think, hey, 3 of each seems nice and balanced. Let's do that. And that plan works. It doesn't break any of our rules. But let's run the numbers. 3 times $40 is $120. 3 times $30 is $90. Add them up. You get $210. That intuitive decision just costs the company $10. Now you might think, $10, who cares? But that's $10 every single production run. Over a year, that little gut feeling could add up to thousands of dollars in lost profit. That is the price of guesswork. All right, let's wrap up with something that is absolutely crucial. Let's talk about how to not mess this up. Linear programming is an incredibly powerful tool, but like any precision instrument, it only works if you use it correctly. A tiny mistake in your setup, just one number in the wrong place, can send you down a completely wrong path. You'll get an answer that looks right on paper, but is a disaster in the real world. These are the classics, the errors I see over and over again. Let's take that first one, mixing up rows and columns. That's not just a typo. If you accidentally tell the model that product A uses machine hours the way it uses labor hours, you fundamentally misrepresented your factory. The model will give you a perfect, mathematically correct answer to the wrong question. So you'll confidently go and implement the wrong plan and lose money. The same goes for misinterpreting the final answer. The math says x equals 4 and y equals 2, but you tell the factory to make 4 of B and 2 of A. The math was right, but the business instruction was wrong. The model is only as good as the person building it and interpreting it. I really want this idea to stick with you as you move into your careers. In this class, if you make a calculation error, you might lose some points on an exam. It's not the end of the world. But out there, in the business world, a calculation error means a lower number on the balance sheet. It means real money lost. The market doesn't give partial credit. The attention to detail we're practicing in here isn't just for a grade. It's training for the precision that the real world demands. Your attention to detail is directly tied to your ability to create value.
So we use this entire framework today to solve a manufacturing problem, but I want to leave you with a final thought. This logical structure, defining variables, setting an objective, mapping constraints, it's everywhere in business. How should you allocate your marketing budget across different ad platforms to get the most customers? That's a linear programming problem. How does a shipping company route its trucks to use the least amount of fuel? That's a linear programming problem. How does a Wall Street firm build a portfolio to maximize returns for a certain level of risk? You guessed it, it's an optimization problem. Your job as future leaders isn't just to manage what's in front of you, but to see these hidden mathematical structures in the world and use them to create a real, data-driven, competitive advantage.